When I'm in charge of starting this session, and the first speaker is Professor Oliver Kuhn with the talk that is written there, Double Hydrogen Bond Dynamics from Infrared Spectroscopy to Laser Control. Yes, please.
Okay, thank you. Thank you very much. Thanks also to the organizers for getting us together at this lovely place. We have, during the last days, we have heard a lot about exciton dynamics, or the dynamics of electronic excitations in these biosystems. And I will shift gears and come to the nuclear degrees of freedom, and essentially going along with what Gerhard said yesterday. There's not only quantum effects in the electronic motion or electronic degrees of freedom, but also in the nuclei. And well, if you think about where you could expect these quantum effects, you go to the lightest element, which is hydrogen. And well, indeed, a lot of quantum effects have been observed for hydrogen bond motion, which is everywhere in these biosystems. And well, this ranges from simple things like zero-point energy to tunneling, up to tunneling at room temperature and enzymes or so, are up to coherent wave packet motion of hydrogen bonds, which has been triggered by infrared, ultrafast infrared lasers. I will come to a particular point here, which is related to double hydrogen bonds. Okay, so there's normally you think of a hydrogen bond like AHB or so, but when you go to more complex systems, you are quite often have double hydrogen bonds. So this is a double hydrogen bond, intramolecular double hydrogen bond in a molecule which is called porphyrine, which pretty much reminds you on porphyries. I will come back to this one later. There are intermolecular hydrogen bonds, like here in this formic acid dimer, which is supposed to be something what mimics the double hydrogen bonds in DNA. And then, of course, going to the real stuff, to real biomolecules here, double or multiple hydrogen bonds all over the place, like here in the DNA strand, or here that's our photoreceptor with this double hydrogen bond motif, or take like these water or proton wires you have which shuttle protons across membranes, and here you have also multiple hydrogen bonds. And then they're coming to multiple hydrogen bonds, and there's the issue what's different from single hydrogen bond. Of course, then you have two quantum particles moving, and you can ask questions. Okay, well, is the dynamics of the hydrogen bonds, so like the, say, OO or NN distance, is it cooperative or is it anti-cooperative? That is, say, if you have two hydrogen bonds, do they move in a way that both of these distances get shorter and longer at the same time, or the other way around? And if so, what determines this motion? And if you have transfer phenomena, like really proton transfer, hydrogen atom transfer, this is pretty much related to the question whether this transfer is sequential, like step by step, or it's concerted that both particles move concertedly at the same time. And the whole thing is, of course, pretty much influenced by the coupling to the environment, which could be like a solvent or a complex protein environment, or it could be even, I mean, if you just consider the proton motion, could be the environment provided by the molecular scaffold. Okay, that's the background, and I will essentially go through two topics. First is base pairs in solution. I will tell you a little bit about how we approach this with the help of quantum mechanic, molecular mechanic, of this force field, and doing molecular dynamics with it. With the help of this molecular dynamics trajectories, I will talk about geometric correlations in these base pairs, come to the infrared line shape, and then tell you what ultrafast spectroscopy, like pump probe or photoelectron spectroscopy, can tell you about the dynamics of these two hydrogen bonds in base pair. Okay, and then I thought, in order to connect with all these exciton transfer talks, I will show you some example where double hydrogen bond dynamics meets exciton transfer. And that's molecular photonic wires, and I will give you some kind of very preliminary ideas about how to design a switch based on laser-controlled double hydrogen transfer switch for the excitation energy transfer in a molecular photonic light. Okay, but the first topic. So, well, of course we would like to study the hydrogen bonds in the full DNA helix, but this turned out to be quite a formidable task, so we kind of stepped back and just focused on one single base pair in solution. Fortunately, there are experiments available which I will address later on. So in the following we'll talk about the two hydrogen bonds NHO and NHN in this adenine uracil base pairs, and about from these topics which I put here I will mainly address the first one, which is the hydrogen bond dynamics itself and the correlations, and the last one, which is related to how this is triggered, or what's the influence of the environment, that is in this case the solvent, on these effects. And both things will be addressed with the help of infrared spectroscopy. All right. Okay, infrared spectroscopy, of course, the first thing what you can do is you look at the stationary infrared spectrum. All the experiments I'm going to show you are from Sander Watterson. And well, that's the spectrum in the range where you have the NH stretching frequencies of these two hydrogen bonds. If you see it like this one is the low frequency, about 3,200 centimeter minus 1, and then you have this hydrogen bonded NH2 stretching frequency, which is a little bit higher here. And both peaks are kind of broad. One should say that there's also a certain solvent background which had been essentially subtracted, but this gives rise to some of these wiggles here. But overall, you have two broad peaks, and you ask yourself what the first question you can ask is what these two peaks are due to. Here you see the setup. It's due to a chloroform solution, which is this purple thing here, and then you have this hydrogen bond. All right. Okay, so what we did now in order to describe this, the full system in solution, that comes with some side groups here to make it stable and to enforce this Watson-Crick base pairing. We put this in solution with the QMMM force field simulation. That means so we treat the whole solute quantum mechanically, mostly due to the fact that we know that the hydrogen bonds itself are pretty poorly described by force fields, molecular mechanics force fields, so we have to use a quantum mechanical description at this point. And then the whole solvent is treated classically with classical force field, standard Gromos force field, and then there's a trajectory generated which you see here. Okay, so well, what you see is essentially the thermal fluctuations. What you also see is that, well, apart from these fluctuations, the hydrogens stay pretty much for most of the trajectory where they are. So there's only very rarely an event where the hydrogen really changes our position, which is good for when you think back to the DNA, which is good for us that the hydrogens stay where they are. Always our problem with application. Okay, so then all the results are drawn out of a 13 picosecond trajectory, which is for molecular dynamics. People is like extremely short. But for doing this QMMM, it's already taking months of computer time or longer. So it's you have to pay quite some price for having a quantum mechanical description of the solute of the hydrogen bonds. All right. So what we can do with it? Well, first of all, we can of course look at just geometry. So you have the two hydrogen bonds, and then you see basically how the bond lengths, the NN bond lengths here, changes along the trajectory. You have the average here, which is like 3.01 angstrom, and you have these thermal fluctuations. You also have here this quantity gives you the distance from the center. So it's well, here you see it's staying almost it's staying really along the whole trajectory on one side of the original hydrogen bond donor. And also you see that from this cartoon here, this is the average angle for the out of line motion of the hydrogen. It's mostly a linear hydrogen bond. Okay, and the situation is it's not much different for the other hydrogen bonds, so it behaves essentially the same. It's a little bit more non-linear because you also have the influence of the non-bonded hydrogen at this NH2 group. but otherwise, well, you wouldn't be able to make much difference out of these curves. Okay, so what can we learn from these curves now? Or what can we use, or how can we use this trajectory to get information on infrared spectrum? Okay, for this you have to know that when you look at the hydrogen here, moving, say, in this hydrogen bond, then this potential, which might look like so, like a very anamorphic potential along this bond stretching coordinate, so there's no proton transfer in this cartoon here, so that this would mean there's a stable minimum over there. What you see, however, is that when you change this NO or the NN distance, the potential energy surface for the proton motion will be heavily affected, so it will change a lot. This is known for 70 years or so. Here I have a picture out of the very old paper from Hudgens, who studied proton migration in water, and that's basically potential, empirical potential for the proton motion as a function of the distance between the two oxygen atoms in the water. And you see it changes from a single minimum when in this symmetric situation to a double minimum depending on the oxygen distance. All right, so this has, of course, talking about infrared spectroscopy, this has immediate consequence, namely that also the eigen energies or the vibrational levels in these for describing the proton motion or the hydrogen atom motion change with an n distance. Okay, and before I come to this, just as a side remark, concerning these distances, there's the correlation between the lengths of the hydrogen bonds, so the A-B distance, which is drawn over here, and the position of the proton, which is essentially here the position of the center, is following an amazingly simple correlation. So these are just points along the trajectory where you mark the hydrogen bond lengths and the proton position, and you see they are almost all on a line, so it's a pretty much linear correlation. A correlation which, by the way, you find also in if you just look at intramolecular hydrogen bonds, and I just give this because I'll come back to this molecule later on, where these are just different molecules where you do some substitutions here, such as to change the bond lengths here of the NN distance, and you see that all these curves here corresponding to different molecules fall on this simple correlation curve. So there's a very, very robust relation between hydrogen lengths and, say, average proton position in this hydrogen. All right, coming back to the spectrum. So that's what we want to extract out of this simulation data. And for this we now make a model which is essentially kind of second-born Oppenheimer approximation, saying that we separate the high-frequency proton stretching coordinates, like AH here, described as coordinate QS, from all the low-frequency motions of the hydrogen bond. So that could be the hydrogen bond distance, could be also, I mean, it's essentially the heat bath if we want. And in order to understand what's now happening is let's just assume that this is a harmonic coordinate, then you would have, of course, drawn potential curves along this harmonic coordinate, and if you have this motion of this coordinate, this will, of course, then have an effect on the proton stretching coordinate transition, which is called omega-1 0 here. Okay, and then, of course, what you are interested in is then the gap fluctuations, which is just this quantity minus its average. Where does the non-adiabaticity come in? And of course, non-adiabatic transitions at this point is nothing but vibrational relaxation. And for this vibrational relaxation, we don't have a good model right now. And we model this by just a phenomenological time t1 by which this state decays. All right, okay, so then you can, having this gap fluctuation at hand, you can just look in Charles Muckamel's book and find out how you can calculate spectra from that. So that will be the absorption spectrum following from the double-double autocorrelation function, Fourier transform. You put in this phenomenological broadening contribution due to the T1 time. And then you have this line shape function. The line shape function is just this integral over the exponent where you integrate over the fluctuation of the transition frequency. Okay, there's an approximation to that, as you probably all know, which starts from a cumulant expansion of this expression here, and then stops at the second order, and then you get this famous G functions where you can express all the linear and nonlinear response of two-level or multi-level systems in, and this is then the line shape function G given just as the double integral here over the autocorrelation function of this gap fluctuation. We will use essentially the exact form here in the following analysis, and just at some point make a comparison with the cumulant expansion to see how non or higher order cumulant terms appear to play a role here. All right, so how do you then get from the distance, say, or establish a correlation between the distance and transition frequency? I already showed you there's a correlation between distance in the hydrogen bond and the proton position. And we know that the distance in a way should also determine the potential energy curve. So there should be also a correlation between distance and transition frequency. So the way how we did this, that we all along this trajectory at about 20 to 30 points, we stopped the simulation and then generated this potential curve for the stretching vibrations of the hydrogens. And then you see here two typical curves for a very long hydrogen bond. That's a dashed line. You see for this very long hydrogen bond, develops a second minimum, which would be correspond to a proton transfer, but this comes at a very high energy, so you will never reach this at thermal conditions. And then the other curve here is for a relatively short hydrogen bond, and you see how they're different. And you see also the eigenstates here, and what we take from this kind of curve, we take the information about the 0, 1, and the 1, 2 overturn transition, and essentially put this in a curve where we have on one axis the hydrogen bond lengths, and on the other axis the transition frequencies. And by just sampling a number of points here, we can establish a kind of fit through this curve, and which gives us the means to basically use this fitted curve then to assign frequencies to basically an arbitrary dense points along the trajectory, right, and get the fluctuation of the energy gain. One should say that although we will see that we get a very good description of the fluctuations, for some reason we didn't fully understand yet is the overall or the absolute values of these transition frequencies are not that good and come out a little bit too low. All right, so then what you see here is here the frequency, transition frequency 1, 0, and versus on the other line is the hydrogen bond lengths for the two hydrogen bonds. And the curves are almost on top of each other. Just if in cases where you have very long hydrogen bonds, then of course the correlation curve flats off. It's almost a dissociated curve. And so the frequency doesn't get larger anymore. Okay, but this gives us a way to really assign with arbitrary delta t, so to say, this transition frequency fluctuation. All right, and if we now use this line shape theory I presented before, we can essentially get a fit to this spectrum, which you see here is a red curve. And you see there are also some numbers given. The numbers are such that in parentheses, there's just the contribution from the putative phasing, and then this is a contribution including the T1 time phenomenologically, which brings us pretty much, for this case, in agreement with the experiment. How I get this T1 time, I will comment shortly on. And while the description for the NHO hydrogen bond is a little worse, but as I said before, there's also substantial fluctuations here due to the subtraction of the solvent background, particularly in this region of the spectrum. So it's also the experimental values are not really very reliable. All right, cumulant expansion. So what we did here now is then we compared the full simulation which is this dashed line with the result you obtain from the cumulative expansion. And you see for the NHN case, it's pretty much, well, not much difference here. But for the NHO case, the results are clearly markedly different, which could be, or, well, first of all, this means that you have some sort of non-Gaussian statistics for these fluctuations, which could be due to the fact also that you have this NH, let's see. So you have this NH2 group, which has one free hydrogen and one hydrogen bonded hydrogen, and the two are also coupled in a way, so it makes basically some very specific couplings influencing this proton stretching motion coming from intramolecular modes, and this will have some very specific effect on this line shape, which you cannot capture just by the second order cumulative expansion. Okay, but for the NHN case, of course, then once we have this cumulative expansion, we can go and check this autocorrelation function of the gap fluctuations, which is shown here. And by assuming a very simple model, which is this Brownian oscillator model, we can, what we did then is we fitted this correlation function to the result you get from the Brownian oscillator model, just to get some idea what's the distribution of coupling strength here. And we fitted it to about 20 moles or so. And then what you see here is then the distribution of coupling strengths, which is of course dominated by low frequency vibrations, but has also some contributions by medium frequency vibrations, which are, if you look at what kind of normal modes are in that range of the molecule, then these are kind of all these more normal modes which change the distance between the two bases, so the AU distance, and thereby modulating the hydrogen bond lengths. So that pretty much makes sense at this point. All right, now, so far we just analyzed the spectrum, but it doesn't give you a lot of information about these correlations I was alluding to in the beginning. For this we need nonlinear spectroscopy. I don't think we had much talk about this already in the last 2 days. I don't think I have to go too much into detail. So it's basically like third order spectroscopy. You have 3 pulses coming with 3 directions. You have 2 delay times here. And then you look for the phase matching directions. And I will focus on the probe spectroscopy, which is coming in, well, like where K1 is equal to K2. And the signal comes out along K3. And then for the photon echo in the rephasing direction, which is given down here. Okay. For this, I need now to calculate from my trajectory these, essentially signals which come out from the perturbation expansion of the polarization with respect to the interaction with the electromagnetic field up to third order. This is also kind of well known. So you have here the third order polarization, you have the response function, which is just the correlation function, 3-point correlation function involving the Dipole operator. And if you work this out, you find in the eigenstate representation now following that this is, you get 8 terms essentially, and one of these terms is given here just for reference. You see, you have to, this involves multiple integration about these fluctuating transition frequencies, and this we do along the trajectory by just integrating over the time origin T0 and these auxiliary functions up to some final time Tf, which is our propagation loss. Alright, so you essentially can generate all the 8 correlation functions which enter this S3 response function, and then you can get the polarization, and from that you can get the single, as described in the many papers of Schauer-Munkelmann, for instance. Okay, for this, however, we need to not only what we have for linear spectroscopy, but we also need the orbital transitions to get excited state absorption. I told you that we can get the information about the energy levels from the kind of on-the-fly snapshot potentials. And so this adds up then into the following model. Do you have another pointer? It's kind of figured out here. Okay, adds up into the following models. You have the ground state, then you have those two excited states which involve excitation of this hydrogen bond, and then you have the two excited state which involves excitation of that hydrogen bond. And doing the same approximation like the Hamiltonian-Condon approximation, no non-adiabatic transitions. That's the Hamiltonian. And basically then what you need to know is just all possible gap fluctuations which you have between all different transitions which you have in this product. Okay, how can you get them? And well, we look for a simple correlation which makes it possible to efficiently get these correlation functions on the fly along the trajectory. And what we found then is the following, that there's a pretty nice linear correlation between the fundamental transition and the overturn transition. Here for the NHN case, it's not that good for the NHO case, but still it's reasonably described. So you have basically then are in a position to relate the overturn transition omega 2,1 to the fundamental transition, and just by fitting these curves. So in the same way you get the fundamental transition, you right away get the overturn transition to calculate this spectrum. All right, that's first the experimental spectrum for the pump probe. And well, essentially what was the purpose of this paper then was to show that hydrogen bonding in these base pairs accelerates vibrational relaxation. Well, if you look at that paper, you find that, for instance, when you have a free NH vibration, so no hydrogen bonding, then the relaxation in the solvent is like 1.5, 1.1 picosecond. Now, for hydrogen bonding, you add up all the anemonic couplings between the different modes, which kind of make the lifetimes very short. And in fact, the lifetime shortens by a factor of 3 to about 3 upon hydrogen bond. So the hydrogen bonded to base pair, once you excite the proton stretching vibration, redistributes the energy much more efficiently than the free molecule. That's the message. Okay, so what we did now is that we used this curve here to get information about the T1 times which enter our model. And that's shown here, so that's the experiment. Well, one of these T1 times has been gotten from the experiment, the other one is essentially we have obtained by fitting just the probe decay. And so that's then the simulation here. So you see first on that side you see basically the effect of the ground state bleaching stimulated emission of the NHN hydrogen bond. On that side you see the ground state stimulated emission of the NHO hydrogen bond. And this peak here is the excited state absorption due to the NHN hydrogen bond. The one due to the NHO it's in that range, and it's hardly seen here also in that experimental curve. Okay, so from this, well, this I think you might well say when that's fully correct. This is just fitting the experimental data, and in a way we fitted it in order to get this second T1 time here put into a model, and now make a prediction, which is now related to the or which now should relate to the correlated vibrations of these two hydrogen bonds. And this we do with photoneutral spectroscopy. Well, again, I don't think I have to say much about this. It's in the pulsive limit, so it's delta pulses. And then we calculate the heterodyne signal, which is just one of these response functions here. As I said, in rephasing direction. Since we don't have a good model for population relaxation, we better set the time T2, so that's the population evolution equal to 0, and then do double Fourier transform to get the signal. Okay, and that's what the signal looks like. It's a real part, in fact. And what do we have here? So we have like these two peaks, which are just coming from the ground state bleaching stimulated emission. Then we have this green stuff here, which is comes with a different sign. That's just the excited state absorption. Okay, and then we have this cross peak absorption, which is coming here off the diagonal, and well, it's a bit. I mean, like this one is a bit screwed by the excited state absorption. That's probably much clearer here, and that's essentially the as you perhaps know, or gas, it's basically the absorption you get when you first excite one hydrogen bond, stretching fundamental, and then the second pulse manipulates the second hydrogen bond vibration. And now we can look at the shape of this peak, and you see it's clearly stretched along or parallel to the diagonal. That means there's a preferential motion this fluctuations proceed in a way that it's preferentially, when one frequency gets larger, the other gets larger as well. So what means, now coming back to what we say about the relation between frequencies and distances, so the frequencies get larger when both hydrogen bonds are stretched because the hydrogen bonding gets weaker. Okay, so what happens then is that we can conclude from that this fluctuations is kind of positively correlated. That is, the preferential motion is that both hydrogen bonds get shorter and longer at the same time, as opposed to the case where like one gets shorter, the other gets longer. There's a question.
The question is this done from just the rephasing side, or is this rephasing?
This is just the rephasing.
Okay, that just helps me interpret the degree of elongation.
Yeah. Okay, so the kind of preferred or the preferred sort of mode of correlated fluctuations, as I said, is such that both hydrogen bonds get shorter and longer at the same time.
Why do you not add the non-rephasing direction to this to get a pure correlation map? Get rid of the phase.
We could do that. Okay, so that's about the. Actually, I have more data on that, but I just okay. So now coming to the second point, which is after we went through this base pair stuff here, which is related to exciton transfer, as I promised initially, and it's about molecular photonic wires, and I will just try to sketch how this is related to proton transfer. Okay, so there's a lot of artificial, or a lot of attempts to build artificial molecular photonic wires, which is in a way you have some unit here which you excite initially, the energy get transferred along that wire, and then you have the lower frequency, or just you have a downward transfer, and then you have basically a photon coming out here, and effectively you have just transported. Well, you have transported the energy, but what you also did is you transported the photon across a certain distance, and this distance can be whatever, like some 10 angstroms or 10 to 20 angstroms. That's been shown. So there are different ways to do this. This is building up artificial structures out of these porphyrin molecules is due to development due to Lindsay. There's some other attempts by Sauer from Bielefeld, who essentially puts chromophores, builds them into DNA strands, and then builds molecular photonic wires this way. Okay, so what's the question now? If you have a wire, of course you want to have a switch. So what would be the switch here? There are some attempts to switch this kind of systems. So for instance, with UV photoexcitation, you make a UV photoexcitation, trigger some photoreaction, and then kind of build in a switch which kind of breaks or stops the energy flow on that wire. There are other methods which are like via electrochemical oxidation or pH change, but you already see here electrochemical oxidation, pH change, that's supposed to be a very slow process. Okay, we want to have a fast switch, and we come now to this molecule, which looks pretty much like this porphyrine I showed you all the time. Okay, so what's the idea then? If you just think about this transfer to happen via cursor transfer, then you know that you have the double approximation. That's pretty good approximation because these things are pretty far apart. Everything is determined by this orientation factor, which is given here for reference. So now imagine that you would have this porphyrine type of molecule with this double hydrogen bonds built in here, and you were able to switch between this position of the two hydrogens in that position. Right? So what you would do then is you would essentially tilt the transition double moment by 90 degrees. So the question is, and by tilting this by 90 degrees, you would essentially modify the transfer coupling here, and well, if the geometry allows, you would probably be able to have a substantial switching. So the question then is, can we just say, or this is just fiction, or can we just design laser fields which drive the two hydrogens from one side to the other to obtain this double switch? Okay, so there's a point now about this double proton transfer. As I said, there's now the issue about concerted or stepwise transfer, which means just, well, if you think of this in terms of two coordinates, one is the coordinate for stepwise transfer, the other one is for concerted. You can either move the two protons separately, so you go this way around, that's normally energetically more preferable, but it's a longer way, or you can also go that way, just the other way around, or you can go just across the hill here and go to the concerted fashion. Okay, so that's basically the two modes of transfer which are possible in these systems. Okay, so what we did now is to do some model simulation. We adopted some model Hamiltonian form theory from some previous papers. Madachina added the field and some asymmetry. So basically, it's like two protons moving along a symmetric and antisymmetric coordinate and being coupled linearly. So it's essentially like two double minimum potentials with a bilinear coupling. And then we also added some asymmetry because if you want to have a switch, you not want to be like the initial and the final position equal, so that otherwise you would have basically, you wouldn't know where to start and where to go. And so we're looking for molecules which have this property. And then we did, which is of course a total overkill here, MCTDH quantum dynamics. It's like just a two-dimensional program. But probably just shows you that you also can do two-dimensional programs with MCTDH, not only 1,000-dimensional programs. So the idea is, as you probably know, is you expand your wave function in terms of single particle functions, which are, or Hartree products of single particle functions, which are time-dependent. You have time-dependent basis and time-dependent expansion coefficient, which guarantees you like a very efficient and description as compared to the standard way of a fixed basis, so a much more compact description of the wave packet. Okay, and on top of it, we used optimal control theory, just in one line. It's essentially you maximize functional, which is the overlap of your time-dependent wave packet with some target state at a certain time t, given that you have some penalties, for instance, penalty for having having strong fields, and you have also other constraints such as that the size should fulfill the Schrödinger equation. Okay, so that's all described here in that papers. Okay, what comes out? So that's now your initial distribution here. So you're initially on that state, and you want to go to the other state. And if you ask a chemist, he would probably say, okay, well, it goes either through the barrier or concerted or stepwise. So there's this kind of way of thinking in this community that reactions proceed either concerted or stepwise. Which is probably true when you look at, say, rate processes taking place basically at arbitrary long time, so like equilibrium processes and so on. But if you have time-dependent wave packets, you see what's going to happen. It doesn't really look like concerted or stepwise, but what you have here is essentially, well, you see the pulse. So initially it sort of totally redistributes your wave packet over the whole area, and then the second part of the pulse which comes to the end, I mean, you first spread the wave packet and then, I'm finished, and then you refocus it again to the minimum, as you can see here. So it's neither stepwise or concerted, but it's both at the same time because you have a delocalized wave packet. One should say that the double moment is such that you cannot excite the molecule along the concerted coordinates, so you have to, because it's just of the symmetry, so you have to start along the stepwise way. So that's why you start here, but very soon you get everything, and then you have to focus at the rear. That's what this pulse does. So messages, we can switch this proton transfer, double proton transfer system, and thereby switch the direction of the transition double moment. And just to show you well, what kind of the magnitude of this effect is, we took a specific example of some of these asymmetric porphyrin derivatives. It's a porphyrine. To show here, you see the transition double moments for the two positions of the two hydrogens. You see the orbitals which are involved. I'm just estimating the effect just from this first formula. You would obtain a change of the double coupling by about 60%, which considerably could switch off the transfer over that point. All right, so that's just to sum up. I've shown you two examples for our double hydrogen bond dynamics. One was base pairs in solution, and there I showed you how we can look with photoelectron spectroscopy to get information about the correlated fluctuations of these hydrogen bonds. And then in the second example, just a kind of toy model how we can imagine to use the laser-driven double proton transfer dynamics to switch on an ultra-fast timescale of about a picosecond our molecular photonic wire. All right, and with this I end. That's my group. That's Yunan Yan, who is a postdoc, did the first part of the QMM assimilation, and Mahmoud is a PhD student who did the second part on this wires. Financial support comes from the DFG, and I thank you for your attention.
Thank you. Questions?
I was a bit confused at the end, because you were showing us dynamics on one potential surface, and then you had diagrams of homos and lumos.
Okay, so the point is, no, the point is the following. I'm not talking about the change of, in order to make this energy transfer, right? It involves the electronic excited state. So you need to change the dipole transition moment for the S0 S1 transition, right? And this depends on the kind of orientation of the two protons.
Okay.
Right, so what I plot here, that's why this is a homo-numo, just to show what the S0 S1 transition is. And what I plot here is a transition double moment, right? Which is changed upon proton transfer. So you make a reaction in ground state and you influence the process which takes place via the excited state.
I see. Okay.
Yeah.
So, how much does the hydrogen atom actually have to move to make this shift in the porphyrine?
Here,
What's the distance?
it's about an angstrom or so. No, not. Yeah, less than an angstrom.
Okay, I'm just, this is related to the question you had about sort of my thought, because if I look at the structure, it just looks like it has to move a lot less in porphyrine than in the porphyrin.
Yeah,
Is that,
but I think the
does it range?
I mean, if you could compare porphyrin with porphyrine, I don't know the precise value, but oh yeah, okay, let's see. Okay, here. So basically what these points here are essentially these correlation curves you get from NMR relating distances to spectral or NMR shifts and then to bond distances. And these points here are, I think 2 is this porphyrine, then you can, and 5 is about porphyrin. Right, so what just tells you that in this porphyrin the cavity is much wider, and therefore the proton, okay, unfortunately this was just meant to be cartoon, so there's no numbers here, and which tells you that also the protons are much more localized at the donors and acceptors. So that's basically, I think that's porphyrin, and then it's different porphyrines here, which have just make, it's basically just a fact of changing the cavity size.
Okay, and 0 is the center?
0 is the center here.
Okay.
And here it's not 0 because you know they have a symmetric case.
Okay.
There are always some generic questions that come when we deal with proton dynamics. One is how much does quantum mechanics play a role here? That is, certainly in some cases there must be tunneling. In the spectroscopy itself, perhaps it is not very important, but could you pin down what is quantum mechanical about these dynamics? And not unrelated to this question is, what would you predict for systems where deuterium replaces hydrogen?
All right. Okay. So I mean, like, let's come to the second first. So what we did for this molecule, we did the following together with an NMR experiment. So we checked when you replace proton by deuterium, you have this what is called the Uhlele effect. I don't know if this okay. What means just that because you have an anharmonic potential, like just changing the average, the expectation value of by changing the mass of the particle, you kind of slide deeper into the potential. This will change also the coupling to, say, the donor and acceptor.
But this sounds sort of a classical effect, right?
No, it's quantum.
Is it?
It's a zero-point energy effect.
Oh, okay.
Right? You change the zero-point energy, and so therefore you kind of move to different parts of the potential for the ground state.
Okay.
Right? And this, I mean, in this system we looked at this. So then you can play the game like just deuterate one, and then you really see like you deuterate one, and if you deuterate this, you move essentially along that line so that the hydrogen bond gets wider, but at the same time the other non-deuterated, just because they are coupled, gets narrower or wider. Right? So I mean, this is really, it sounds like a tiny effect, but it's measurable.
Okay.
Right? Okay. So there are effects. Essentially, zero-point energy. Of course, then it comes up when it comes to tunneling. Then, but sure, it's awesome. Quantum effects. I mean, of course, this is this is as quantum as it could be, right? I mean, it has tunneling, it has kind of interference, and all that stuff. For the first part, I mean, there's also interesting point. The only thing I could quantify right now or make a statement to is the following. Right here. Okay, what I told you that I'm not very happy with the absolute number of the transition frequencies. So they come out a little bit too low. Okay, so we now do a classical simulation, fully classical simulation. You get out almost quantitative agreement. Which just means that with these DFT potentials, you kind of sample like a range which is just at the very bottom here, right? And just by adding this, what is it, like 5 times KT at room temperature, you are in a different range of potential, and you run into trouble with the 2 sub DFT potential. I mean, it's not really probably a quantum effect what you mean, but it's kind of where you have where it shows up here as a kind of showing the failure of the potentials.
Is there any evidence of tunneling in the sense that it be depending exponentially on the mass?
You mean here?
No, I mean in the general phenomenology. Is there any?
Sure. Yeah. You mean on the mass of the heavy atoms or of of the hydrogen? Sure. I mean, sure. There's also for this focusing, what people that's essentially a way to prove tunneling.
Okay. So
there are experiments where you do electronic excitation, and then you see mode-specific tunneling. You decide some scaffold mode which shortens the hydrogen bond distances. You get a larger tunneling split. Then you replace deuterium by and then it goes smaller again. So there's ample evidence for this effect.
So in your movie of the wave packets evolving in time under the influence of the laser field, it looked like your initial wave packet there looks like it should be time dependent if that's roughly a symmetric potential. What does it look like when it evolves without the laser field?
No, that's a ground state.
It's
not. I mean,
there's an asymmetry in that.
I added some asymmetry to make it localized on one side.
Okay. So that's time-independent state that you're starting with?
That's the initial time-independent state, and I mean, of course, the
Okay, I just didn't see the asymmetry.
it's very small. I mean, you don't want to have it
Sure.
with the barriers low, so you will have like a tunneling back. So you want to have just, let's say, like a 10 or 20 centimeter or so, just so much that you kind of disturb this tunneling splitting, and you not have you have a localization on one side. But of course, the final state is not time independent because it's not an Einstein. I mean, I think the transfer efficiency or the target state, it's like 95%, so you have like 5% you cannot get with those fields.
This nice movie you're showing quantum coherence. Of course, you adopted a two-dimensional model.
Yeah.
The question, of course, that arises if you now would also include more modes,
Yeah.
essentially adding dephasing, adding all kinds of environmental
Sure.
degrees of freedom, whether this guy is alive. And with MCTDH, you even could do it. I mean, you can strip it
Yeah,
apart.
sure. When you could couple it to bath, but we set out to do it, I mean, essentially from first principles.
Yeah.
And this is not that easy to generate a Hamiltonian for that. Or at least we are not that far. I mean, I know what you mean, and it's in a queue. That's why I'm saying it's a toy model at this point.
Mm.
But what you essentially want is for this molecule you generate a full dimensional Hamiltonian.
Yeah.
We're working on it.
So in terms of the quantum mechanical treatment using density functional theory, one concern about hydrogen bonds is that they could require sort of a multi-configuration treatment. I mean, do you think the B3LYP is, because it's an asymmetric hydrogen bond, do you think the B3LYP does a good enough job, or?
Well, actually, we are not in solution, but we tested this in the gas phase with MP2, which has also, I mean, the other issue is like a dispersion correction,
Yeah.
which should play a role, it's not a stack-based pair, but still there's some effect. But essentially, if you judge from the transition frequencies, you get probably 100 centimeter minus 1, which due to a bit shorter distances. So it's not it's within the probably all error. So it's not really a major concern.
Okay.
And the plot you showed where you were correlating the fundamental and the overkill lines.
Yeah.
You said that there's a good correlation for the symmetric case and then not for the non-symmetrical case. Can you explain simply why that arises?
Okay, let me just.
Yeah.
Okay, so you're
I mean, is there a simple reason why the scatter in the unsymmetrical case is larger?
Okay. First of all, I should have pointed out that these are experimental points here, so which we also use as fitting. Okay, to answer your question, I think much of the trouble also when it comes to the when it comes to the kind of non-Gaussian statistic and what I meant with specific coupling is due to the fact that this motion, I mean, this group is much more floppy than the say compared to this NHN. So you have a coupling to the other NH stretching vibration here, and which kind of I mean, like this kind of moving. I mean, you've seen the movie, right? Like the whole thing is moving. You have a coupling between the two stretching vibrations, which makes it. I mean, probably one should have like a full description of the whole group here, which would be much better. And I think that's part of the larger scatter, so that it doesn't follow really simple linear correlation. I think it's all about the anamonic coupling in this amine group.
This is a very system-specific effect.
It's very, when you see like for this case, which is more rigid, it works perfectly, right? But for that case, which is more floppy, it just doesn't work.
So it's because you're dealing with this system and you have that particular amine group with so it's the two NH stretches on that amine.
Right.
Yeah. Okay. It's
Actually, we also did we generated two-dimensional potentials.
Right.
On these two colonies, but it didn't really give much improvement.
Okay.
Other questions?
Fanny, thank you very much for your speech. And we are going to the pitch.
Right, let's take the conference. And you meet back here at 11 after the conference.